Hello students, in this video let us discuss some more important questions for JEE advanced exam. We are very close to the final exam. So your first question about the keto-enol tautomerism. So which compounds are stable in enol form than keto form? So you know very well about the acetyl acetone. This is stable in enol form. So that is stabilized by the intramolecular hydrogen bonding as well as continuous conjugation, you know that. So next here, this compound is stable in a keto form. Why? Because for this compound there is no hydrogen bonding, just there is a conjugation. So here in this case this compound is stable in a keto form but not a but not enol form. That means of course it may has enol form like 20 or 30 percentage, but here more than 50 percentage keto form exists for this form. Okay, and next here one more compound, this is a carbon and a hydrogen is there, so this can be enolized. So here in this case enol form is like this. That means in enol form for this compound, here it is a stable enol form for that compound than the keto form. Enol form is stable. Okay, so this example is given in a Jonathan Clayden. So almost all these examples I have collected from the Jonathan Clayden. Okay, so in this case why this enol form is stable, why this not that keto form is not stable? Because here this carbon is the sp3 carbon. That sp3 carbon means here 109 degrees bond angle. Okay, so here it is a bulky group, it is a bulky group. The angle means 109 degrees, it is a smaller angle between the two bulky groups. But here in this case between these two groups nearly 120 degrees angle. Okay, because of the that sp3 carbon after enolization converted to sp2 carbon, so your bond angle increases, so the repulsions between these two bulky groups decreases. So that's why enol form is dominates than the keto form. And next this one, this tri-keto form is stable in, that means keto form itself stable in keto form. Here in this case enol form is not dominating for this compound. Okay, so why? Because this compound has a three keto groups, and three keto groups are not adjacent each other, so there are no repulsions between similar charged carbons, and this C double bond has a higher enthalpy formation, so a keto form has the most stable for this one. Okay, even though enol form has an aromatic nature, so but here in this case for this compound here enthalpy formation of the C double bond is higher. Okay, that means here the keto form is dominating than the enol form. Now here the similar example of these three, here in this case partial positive charge, here partial positive, here partial positive, here more repulsors, very less stable keto form, so that's why it is stable in enol form. And here for this compound, what is the enol form actually? So here double bond O, first of all here OH, here OH. Okay, this one has the enolizable hydrogens, this one has the enolizable hydrogens. Now here by the 1,5 shift here these protons also transferred, so here we will get the enol form. This enol form is a more stable enol form. The pi bond here OH, here pi bond here OH, more stable enol form. Because in this case here, even though it has a three C double bond O groups, but here more repulsions between the similar charged carbons. That's why here that is more stable in a enol form. Now we are coming to this compound here, also same story here, positive repulsions, so this compound also stable in enol form. Here OH pi bond, here OH pi bond, for this one OH. Okay, this one also has a stable enol form. Now here in this case this is the hydrogen, so it can be enolized. So here the enol form is nothing but ascorbic acid. This ascorbic acid has a more stable enol. Okay, that's it, the ascorbic acid. And in this ascorbic acid you know that this hydrogen is a more acidic hydrogen. Okay, and it is this enol is stabilized by the continuous conjugation. So ascorbic acid has a stable enol form. Now here in this case, this one also has a stable enol form, because if you read the enol form for this compound here, OH, here double bond O, here there is a hydrogen bonding and as well as continuous conjugation is there. So that's why this compound is stable enol form. This compound has no stable enol form, but this compound has a stable enol form. And you know that ester ester has a less percentage of the enol form. So finally here A and C, here H, G, F, E, all these have stable enol form. Okay, that's it. And next, yeah, this one more question. So here in this case, first of all, this Na plus OET minus, ETO minus, it is a base actually. That base remove the proton from this alpha carbon. So here we will get the carbanion. This carbanion is stabilized by the resonance. So we will get the enolate ion. Enolate ion. So now here, by reacting with the acid halides, here generally there is a partial negative charge, here there is a partial positive charge. So this carbon has a more positive charge. So this positive charge, more positive charged carbon attacked by the more negatively charged atom, that is oxygen. So leaving out the Cl, so here double a bond O, here O, here this is the compound in this case. Okay. Now here, the one more point is, for this compound here, the partial negative charge is partial positive charge. Okay, so here this positive, here magnitude of the positive charge is very less, so that's why it is attacked by the less negatively charged nucleophile. So that's why here in this case alkylation takes place on this carbon, but in this case by reacting with the acid halide, that is attacks on the this one. Okay, because your oxygen is a smaller size atom, so that has a more electron density. Your carbon is somewhat larger in size, so that has a less magnitude of the negative charge. So less magnitude of the negatively charged carbon attacks on the carbon which has a less magnitude of the positive charge, but your oxygen has a higher magnitude of the charge, so that attacks on the more positively charged carbon atom, that is a that means a carbon of the this group. Okay, so that's it. This is the product ultimately. So next here one more question. So Br2AlCl3. So actually here if you take the benzene, the Br2AlCl3, you will get the bromobenzene. Okay, so H plus replaced by the bromine. But in this case, first of all, this Lewis acid, that Lewis base attacks on the Lewis acid. So this one OAlBr3, this one carries a positive charge, this one carries a negative charge. That's it. Now here these hydrogens are enolizable, so enolization takes place. So here bond COAl Br3, here negative charge, so double up bond. That's it. Now here in this case Br plus attacks on this one, so reformation of the pi bond. So these alkynes are transferred to this carbon, and this negative charge carbon attacks on the Br plus, leaving of the Br minus. So here the ultimately the product is alpha halogenated product. Okay, and then here remaining one Al Br4 minus, because here Al Br3 attacks on the Br minus, so we'll get the Al Br4 minus, and here alpha halogenated product. Okay, so here substitution does not takes place on the benzene ring, because the Lewis acid here carbonyl group here, so because of this Lewis acid base complex formation, these hydrogens are easily enolizable. So here then by the successful reactions we will get the alpha halogenated product. Okay, that's it. Next here one more question, that acid halide on reaction with SOCl2 will get the carboxylic acid on reaction with the thionyl chloride will get the acid halide. So here generally this acid halide hydrogens are the enolizable, so enolization takes place. Now this enol form on reaction with the bromine, so in this case this carbon attacks on the Br plus, so we'll get the that double bond OCl here, in this case Br. Okay, so here by writing the resonator structure for this one, so this one carries a negative, chlorine, and here in this case OH plus. Okay, so this negatively charged carbon attacks on the Br plus. That's why here finally in this case that hydrogen replaced by the Br. Okay, that's it. That means here H plus is replaced by the Br plus. So it is a one type of electrophilic substitution reaction. Now on reaction with methyl alcohol actually. Okay, so here methyl alcohol, this one oxygen attacks on the more positive charged carbon. So that's why here that Cl is replaced by the OMe actually. Okay, by next class of HCl takes place. So here in this case this one actually here acid halides are more reactive towards a nucleophile attacking than the alkyl halides. So here in substitution reactions, okay, in substitution reactions acid halides are more reactive than the general alkyl halides. Okay, acid halides are more reactive towards nucleophile attacking than the aliphatic alkyl halides. Okay, so previous question, that is a NSCC question. That's it. And next one more question, that is regarding the SN2 reaction, which is more reactive in SN2 reaction. So that means here first of all here let us try to write the Chair form. So tertiary butyl equatorial position, and that means here both are cis, so the upward direction it means equatorial. So here in this case OTS upward direction, so upward direction, and equatorial axial, it is a cis form. Now for this one tertiary butyl bulky group, that must be in equatorial position, that means upward direction. So trans, if it is upward, then here OTS must be downward. So here equatorial is a trans form. So which is more reactive towards nucleophile substitution reaction, that is a bimolecular reaction. So that means here in this case that SN2 reaction takes place through the transition state. So here in this case that whenever the leaving group is in the axial position, that is more reactive, that is more favorable for the nucleophile attachment. So a nucleophile can attack from this side. If it is attacked by the nucleophile from this side, this one experiences repulsions with the hydrogens, axial hydrogens. That means whenever a nucleophile attacks on this carbon, so that facing repulsions, that means 1,3 diaxial repulsions. So that's why here this conformation, this compound does not favor the SN2 reaction fastly. But in this case, whenever this group is in axial position, so here actually this one favors the SN2 type attacking, because in this case by attacking of this nucleophile, here leaving out this OTS takes place. So here very less repulsions, but in this case the nucleophile coming to form a bond. Okay, so that nucleophile facing a more repulsions with these hydrogens. Okay, but in this case here breaking takes place, that is a leaving out, so here the repulsions decreases in this case. That's why nucleophile favorably attacks at this carbon. Okay, so here this compound is more reactive towards SN2 type reactions, that means towards nucleophile attacking. Okay, so of course here after nucleophile attacking you will get the product like this. Okay, so this is a nucleophile, that means here this nucleophile attacks from the below the plane, so we'll get the trans isomer. Okay, that's it. Next here one more question. This is the Ido Form reaction. So you know that this first of all here this ONA and CH3, that is the Ido Form reaction. But in case of the bromination in the presence of acetic acid, that means here in acidic medium enolization takes place. So in acidic medium 2 enols are exist. Okay, so actually which enol is stable? This highly substituted double bond, that means it is a more stable. So now here this one attacked by the Br, so here transfer of these electrons, this carbon carries a negative charge, this negatively charged carbon attacks on the Br plus, leaving of the Br minus, here leaving of the H plus. So here finally we will get the alpha halogenated product. Okay, it is a major product actually. It is formed through the stable enol form. Now here NaNO to HCl, from this one we will get the HNO2. Okay, HNO2. Now here from the HNO2, by treating with HCl, excess of the HCl, we will get the H2O plus and NO. So by loss of water molecule, we will get the NO plus. Okay. So now here this NO plus is the electrophile. In acidic medium, this one exists into more stable enol form like this. So now here the transfer of electrons takes place. This carbon gains negatively charged, that means negative charge. It is a nucleophilic. So this nucleophilic carbon attacks on the electrophile NO plus. So here in this case, that means OH carries a plus charge. Here in this case N double bond O. So just here loss of proton. So you will get the alpha nitroso compound. So here it is again ionizable hydrogen. So double bond NOH and double bond O oxygen actually. So here this oxygen on further hydrolysis, the oxygen on hydrolysis will get the hydrogen here, a hydrogen, that means here diketo compound is the product. Okay, on the hydrolysis, that oxygen converted to ketone. Okay, that is one more question. So next here, okay, let us discuss these aromatic reactions in next video. Yeah. So here in this case, phenol on bromination, we will get the tribromo compound. Okay, that means here bromine OH. So sorry, that is a Br, here Br. Okay, so in actually polar solvent we will get the tribromo compound, but in non-polar solvent we will get the monobromophenol, that OH parabromo and OH here orthobromo. Of course here parabromo product is a major. Okay, now in similarly in case of the aniline we will get the that tribromo product Br and Br and Br. Okay, now in this case Br and carbon disulfide as in the case of phenol, but your product is completely different because that NH2 is a strong donating group than the OH. That's why here also tri substitution takes place. Very important point here. Just some key difference here. Phenol on reaction with the bromine in a carbon disulfide will get the monobromo compound, but aniline on reaction with the bromine in carbon disulfide will get the that even tribromo product. Even it is a non-polar solvent, but we will get the product as in the case of polar solvent. Okay, if you take that means we can take here water or polar solvent like acetic acid, so we will get the that same product. Okay, that's it. So next, the phenol on reaction with the dilute HNO3, nitration takes place. So orthonitrophenol 36% and paranitrophenol 25%. Now here the toluene on bromination will get the 60% of the ortho product and 35% of the para product and 5% of the meta product. So here orthobromotoluene is the major product. Now next one here, toluene on reaction with the chlorosulfuric acid. Here will get the that means chlorine compound containing chlorination. That means chlorosulfonyl chloride. Okay, so here in this case you know that this is a PTS, a para toluene sulfonyl chloride. Okay, that is nothing but Hinsberg reagent. You know that. So here in this case, why this one actually here the Cl S double bond O, this one double bond O, here OH plus OH S double bond O, here double bond O Cl. In this case actually here self protonation takes place, double bond O OH, here H plus this one lose the proton to this one. So here by loss of water molecule we will get the SO2Cl electrophile. That's why SO2Cl electrophile attacks at ortho position as well as para position. But in this case here for ortho, almost here that para product is, that means ortho product is major. Why it is ortho product is major? Because here methyl is the donating group, that gives more electron density at the ortho position. That's why this alcohol readily attacks on the ortho positions. Okay, that's it. And next some more reactions. So when benzene on reaction with the H2SO4 HNO3 you will get the nitrobenzene. But here when using concentrated HNO3, that means concentrated H2SO4 and fuming HNO3 at 100 degrees centigrade, you will get the dinitro product. Actually mononitration. Next anode group is a meta directing, so incoming alkophile attacks at the meta position. Okay, so at a high temperature the fuming HNO3 we will get the meta dinitropenzene. Now nearly again here at 160 degrees centigrade we will get the trinitrobenzene. That means here NO2, here NO2, here NO2. Why you have to require the more temperature? Because here by the replacing hydrogen by the NO2 group, that reactivity decreases. That's why here step by step for nitration we need high temperature. Okay. So now here this phenol on reaction with the constant H+4 at 100 degrees centigrade, again here disulfonation takes place. Okay. So of course here we know that the well-known that synthetic application of this one. So by the bromination in carbon disulfide we will get the monobromo product, that SO3H here, SO3H here, Br. Now here this sulfonated product on heating with the dilute acid, desulfonation takes place. So here we will get the orthobromophenol as a major product. Okay, that's it. Of course here this compound on reaction with the excess of the bromine and water, so all SO3H groups are replaced by the Br. That means here tribromo product. Okay, these alkophiles, that means SO3H alkophile replaced by the Br plus alkophile. That is nothing but ipso substitution actually. That is nothing but ipso substitution. Okay, that's it. So about the ipso substitution we will discuss in a separate video. Now here next this one. So actually here this allyl halides are not involved in a substitution. Okay, you know that this allyl halide on reaction with methyl alcohol, no reaction. Of course if any other nucleophile substitution is not possible, but in this case because of the conjugation, whenever this pi electrons transfer to this carbon and this electrons are transferred to oxygen, this one carries a positive charge, so that is readily attacked by the nucleophile. So Cl here in this case OMe and hydrogen, this one carries a positive. So here in the case O minus, so here pi bond. And next here that proton transfer, so Cl here OMe and in this case OH, so benzene ring, and then here this enol form converted to keto form, that means like this, like means so here reformation of pi bond, here transfer of electrons and leaving of the Cl minus, this one carries a negative charge, by leaving of the Cl minus this one carries a positive. So here OMe and double bond in azial position, so here double bond O and here phenol. That means here ultimately the Cl is replaced by the OMe. It is a this is actually substitution actually. Okay, so addition followed by substitution. So first of all nucleophile is involved in addition, then here elimination of this one. So finally here this is the addition elimination mechanism. So through the addition elimination mechanism here substitution takes place like AR SN2 type reactions. Okay, here also same through like this example. So here Cl is replaced by the NH that means here in this case the product is double bond O, here NH pH and here also NH pH. Okay, that's it. You get the double bond also. Okay, next yeah, here also one of the beautiful question. So here acid base reaction takes place, this one has a basic nature, so you'll get the strong nucleophile. Here the two chances actually, this nucleophile attacks on this carbon, so here the product is pi bond here, in this case OPH. Okay, so here this is a charged nucleophile, it is a primary carbon, it is a tertiary carbon, so this nucleophile majorly attacks on this primary carbon. Okay, that's it, this is the major product actually. Okay, that's it. Now here in this case, here this is the nucleophile. Okay, this is a nucleophile. Nucleophile may attacks on this carbon, it is a secondary carbon. Okay, so actually in a SN2 type reaction the primary that SN2 reaction mostly takes place on the primary carbon. Now here by leaving of Cl minus, this one partially carries a positive charge, so by transfer of this pi electron this carbon carries a positive charge. Okay, so this positively charged carbon may attacks on this nucleophile, or this positively charged carbon may attacked by this nucleophile, but here in this case on the secondary carbon, here in this case primary carbon, so substitution majorly takes place on this carbon. That means here double bond here, this N ethyl and this nitrogen carries a positive charge. Next here by loss of that H plus will get this product. That means it is a SN2 prime type reaction. Okay, SN2 prime reaction. Here in this case direct SN2 reaction. Okay, but in this case SN2 prime reaction, that means here that nucleophile, that new nucleophile is not bonding to the carbon which has a leaving group actually. Okay, that is bonding to the other carbon in the molecule, so that's why it is a SN2 prime reaction is called as. Now here in this case, it is a NaOH is a basic solution. So a basic solution here, nucleophile is generated. So this nucleophile here actually by leaving out Cl here, there is a primary carbon, is secondary carbon. So directly this one attacks on the primary simple carbon. So that means it is a SN2 type reaction. Okay, now here you can see here in this case, this example, so this Cn minus may attacks on the secondary carbon, but here through the conjugation this can attack on the primary carbon. So here attacking on the primary carbon is more favorable. So that's why you can call this one SN2 prime reaction. So actually here by direct product is this one. So but in this case this is a major product. So because the secondary reactions, that SN2 reactions mostly takes place on the less hindered carbon. So it is a secondary carbon, so a little bit hindered carbon. It is a primary carbon, less hindered carbon. So Cr minus majorly attacks on this carbon. So by leaving out the Br minus here, this one carries a positive charge. Then migration of this pi electron, that means moment of shifting of this pi electrons. So this one carries a positive charge, that is readily attacked by the Cn minus because a less hindered carbon. Okay. So it is SN2 prime reaction. Okay, that's it. So next